This is a demo about how vDefend's distributed IDS and IPS's unique architectural advantage provides unmatched capabilities to protect against AI-driven attacks. Frontier AI enables threat detectors to discover exploitable vulnerabilities at a volume and velocity we've never seen before. Advanced AI models are also great at automating the chaining of exploits and customization of tools and techniques to enable an attacker to propagate an attack at machine speed. I'll walk through an example here of an AI-driven attack, and in this case, an attacker gained initial access into the environment via stolen credentials, bypassing the perimeter firewall and making it irrelevant. From there, they chained together exploits and other techniques to quickly gain access to critical resources deep inside the network. I'll then show how through distributed virtual patching, we can immediately address these vulnerability exploits, giving organizations time to apply their software patches while remaining protected. Frontier AI models have turned initial access into a commodity, frequently bypassing the perimeter, entirely using automated, highly targeted credential stuffing or flawless spear phishing. The attacker slips behind the firewall to secure a beachhead on the internal user endpoint. The critical takeaway here is an architectural failure. In a flat network, the moment the perimeter is breached, the attacker inherits trusted visibility over your most critical internal workloads. Once the attacker has bypassed the perimeter firewall, the attacker could take advantage of the lack of internal segmentation to map out the environment and discover vulnerable workloads, operating systems, and protocols. Given the velocity of vulnerability discoveries with Frontier AI, this becomes an exponentially bigger problem than we've seen in the past. In this case, we can see the attacker was able to discover application vulnerabilities in the automation platform, as well as OS and protocol level vulnerabilities elsewhere in the environment. GenAI models also excel at scanning application architectures and instantly calculating how to chain distinct, lower severity flaws into unstoppable maximum severity attack vectors. By automating linking an authenticated file read with a runtime sandbox escape, the adversary transitions from having zero credentials to full remote system execution in milliseconds. Relying on traditional manual code patching is a losing battle against an AI that chains exploits at this speed. We must break these attacks at the infrastructure layer. So how can we help organizations deal with the tsunami of vulnerabilities and machine speed of attacks that are coming at them? Virtual patching provides the first line of defense for our customers and can be applied in 3 easy steps, starting with assessing what the critical vulnerabilities are through a third-party vulnerability assessment. Then the application of a fine-grained virtual patch right at the network interface of the vulnerable workload. And finally, a detect and prevent policy is put in place to stop the exploit right in its tracks. Here's an example of a Nessus vulnerability scan that shows a number of critical vulnerabilities are discovered in the environment, with one of the top vulnerabilities here concerning a vulnerability affecting the automation workload. Once vulnerable workloads have been identified, customers can use the vDefend threat intelligence service to confirm what signatures we have available to virtually patch those vulnerabilities. We can then apply a tag to the vulnerable workloads and create a grouping based on that. As of vDefend 9.1, we have the ability to create an IDPS profile that specifically includes vulnerabilities based on a CVE. Our third step is actually configuring the virtual patching rule, which applies the IDPS profile to the vulnerable workloads. A benefit of this very granular application is that we protect against the identified vulnerabilities without introducing risk of false positives or noise compared to traditional IDS and IPS solutions that apply a broad set of signatures everywhere. Once the virtual patch is in place, even if the attacker had gained initial access into the internal network, we prevent the vulnerability from being exploited and being used as a launchpad for other attacks deeper into the network. Here we can see that the attacker attempted to exploit this automation vulnerability, but was prevented from doing so by our distributed virtual patch. Beyond virtually patching this specific workload, we can apply virtual patching to other vulnerable workloads. In addition, customers can use the distributed firewall to reduce the attack surface and contain vulnerabilities. Furthermore, the full ATP stack within DR enables detection of rapid and autonomous exploit changing across the network.